Okay. So we are going to continue the discussion with the fins and the multidimensional conduction. But before that, we are going to talk about the project a little bit. I have uploaded all of the rubrics and the guidelines and templates, whatever you need. Also some previous semester's projects, samples, essentially online. You can check them out. The one that I have uploaded doesn't follow all of the formatting guides that I have put on the guideline and rubric, but it's a pretty good one. So you can just copy and paste the one that I uploaded. I didn't have a better project, right? So no one did the best job, as is usually the case. Let me put this one on. Okay, so let's talk about your guidelines. They are posted on Blackboard, so you can, of course, go and download them and read them. These documents are on Blackboard. So the first part, of course, the step one of the project was to choose your topics. I'm hoping at this point, today was the deadline, right? At this point, you have already chosen your topic. And some of you have actually discussed it a little further. Some of you have prepared a semi-proposal, like to make things a little, I guess, clear for me. And I've had a couple of coaches. I'm meeting with two groups next week and tomorrow to discuss the project a little further. So you can start. I mean, it is not a bad idea to start working on your project sooner than later, right? But you can always change the topic before the proposal submission. I mean, even after the proposal submission. So make sure to get a head start on your proposal. And next step, which is the next step, and it accounts for 20% of your total project grade. Okay, proposal is a very important step in your project. I may ask you to change, or I mean not change, but to refine your project topic after I see your proposal submission. I may tell you that this is a very complicated project, or this is a very easy project. It needs to be a little more complicated, right? It doesn't mean that we are going to change the title altogether. I may just ask you to add something to it or remove some parts of it, right? And at this point, I don't really see any issue with any of the topics. So all of the topics you have sent me are, we can work with all of those topics. It really depends on your proposal at the end of the day. And the due date for the proposal is sometime in February. Is there anyone who has a syllabus? Tell me what is the due date for the proposal. Can I borrow that for a second? Thank you. Yeah, so if you go to your syllabus, as we have discussed before, you have all of the due dates there. Your proposal submission deadline is February 17th. So in, I guess, 3 weeks, right? And what do I need for that proposal? Of course, it has to be a full report, no more than 5 pages. If you have to go more than 5 pages, sure, you can go 6 or 7. Well, I would rather to see a very short proposal. And if you end up staying in academia and writing proposal for grants, they definitely want you to be as short as possible, as precise and short as possible. Our proposals are a little more detailed than a grant proposal, but they are in the same spirit. So you need to have a title page and authors page, of course. I have uploaded a template from AIAA, which is the aerospace engineering organization, I guess, the same as ASME was in aerospace engineering. You can follow any template. You can follow ASME templates. You can follow IEEE templates. It doesn't really matter. You just have to tell me that I'm following this other template instead of AIAA. But they are essentially the same thing. You have to include the nomenclature of whatever you are using. There has to be an introduction in your proposal. You have to introduce your work, and you have to introduce the other's work on this topic or close to this topic, right? Think of this whole project as a practice for writing industrial report or journal papers, right? Of course, this is more geared toward journal papers than the industrial reports. So do your job, right? You have to review at least 3 papers that are either on the same topic or in the same field of your topic. Then the next part is the proposed method, the methodology you want to use in your project, right? Do you want to do numerical simulation? Do you want to do experimental simulation or analytical solutions? It is very hard for me to accept an analytical solution for a project, and I have one group who is trying to convince me that this is a good way of looking at this course project. But I mean, at this point in time, analytical solutions don't really bring anything new to the table, so it is very hard for me to be convinced by an analytical solution. But I mean, if you have you can bring your best team forward, of course, and try to convince me. Then I assume you have some expectations about what you want to see as a result, what you think you're going to see after you do this project. If it's an optimization, you're going to expect, I guess, you're going to expect whatever, heat transfer rate to be better, to get better, right? This is what you may eventually end up concluding the exact opposite, but that is all right. What you expect and what you get can be different. And then you have to provide a Gantt chart or a project timeline. Do we know what a Gantt chart is? Yes. Is there anyone in class who doesn't know what a Gantt chart is? Yes. Okay. So there is a template of the Gantt chart. You can do it in Excel. Pretty easy. But essentially, a Gantt chart tells you the timeline of different parts of the project. I will open the Excel. I don't think I have Excel in my iPad. So this is let's see if this opens. It doesn't open very well, but you can go on Blackboard and download that template. You essentially have to tell me that which part of the project should be done by what time, right? What is your expectation? Of course, there is a deadline I set for you, but you set a deadline for yourself, right? I assume you want to be done before my deadline to fix any problems that you may see in your project, okay? So there has to be this Gantt chart, and eventually you have to include your references, right? You're reviewing literature, you're using some textbooks as your reference, you have to include all of those. And at some point, can I borrow your syllabus again? Where did I put it? I'm sorry. At some point, you have to write a progress report, because I want to make sure that you are working on this and you are not postponing this to the end of the semester. And the deadline for that progress report is March 24th. So it is after the spring break, 2 weeks after the first spring, 1 week after the spring break, and after your exam 1. You have plenty of time to work on your progress reports. For your progress reports, you just have to add on to your proposal. You don't need to write anything from scratch, right? And I expect to see an updated Gantt chart based on your progress so far, and some results and discussion. If you need to course correct by your progress report, sure, you can definitely do that. If not, you'll just continue working on your project. And then the final report, the progress report is 10%. Then we have the final report, which is 30% of the whole thing. And you have to include all of these sections in your final report. So you're going to, instead of the expected results, you are going to add a result and discussion and a conclusion to your paper. And it shouldn't be more than 10 pages long. And for this one, this is a hard limit, right? So if you go past 10 pages, you will be penalized. You will lose some points, right? You have to stick to the page number. You have a presentation. Again, for that presentation, I've uploaded a template. You don't need to follow that template. It's just a regular AIAA template again. You have to give a 15-minute presentation. Of course, everybody in your group has to participate in the presentation. Then the audience will ask questions. When the time comes, I'm going to let you know. I mean, I can tell you right now that asking a question will land you a bonus point. So make sure to ask questions during others' presentations. Giving them a harder time will give you more points. So, no, I'm just kidding. But asking a question will give you a bonus point. It does have to be a good question, though. Yes. Why was the color red? Is not a good question, right? On a heat map. So, not just any question, a worthy question. And eventually your presentation grade. Some part of it, I guess I have mentioned here. 30% of it will be the presentation itself. How well you have built your PowerPoint, right? If you have followed the template or not. I mean, if you have included everything, if you have the good results and discussion section, right? That's just 30% of the presentation grade. 70% of it is your presentation on how you present your work, right? And your mastery of the topic. This is where I figure out which team member has worked the most, right? And eventually 20%, I think it should be 10%, right? Let's see, we have 20 here. It should be 10%, yes.
So suppose two people present for a group, will they have the same score or can it be shared differently?
It is different. Your project grade can be very different, yeah. Okay. It all goes back to your presentation actually and your peer evaluation. Peer evaluation should be 10%. That's a mistake here. I should fix this. This is 10%, right? 20, 30, 50, 20, here, 70. No, it should be 20%. That's correct. 20%. Why did I think this should be 10? 20% is peer evaluation. I will send out a Google form after you're done with the presentation, right? And you have to fill out that form. And in that Google form, I'm going to ask you about your teammates. So if you give them a good grade, they will get a good grade out of this peer evaluation. If you get them 0, they will probably get something close to 0 on their peer evaluation grade, right? So if this is your chance to screw your teammate essentially, if you want to. Is this clear? Do we have any questions about the project? Okay.
Totally, how much percentage will be allocated to the project?
The project is you have it on the syllabus. If you go to the grading policy section of the syllabus, it tells you that your project is 20% of your total grade. It is right here.
Yeah.
So that 20%, if you get a 0 on peer evaluation, 20% of that 20% is essentially 4 points, right? 4 points out of 100. But I mean, if a teammate gets a 0 on their peer evaluation, I assume they're gonna screw on their presentation as well, and I will probably ask them to come in and explain that 0, right? Or explain their contributions. I'm not gonna tell them that they got a 0, of course. But yeah, I guess you know how it works. Yeah? If you're part of a team, do your job and pull your weight. That is just this peer evaluation grade is to make sure that everyone has done their job. Any questions? No. So everything, yes.
I was thinking that the teammates have to share the work based on their strength. I don't know if you understand me.
I didn't hear the question.
So the question I'm asking is that suppose I'm with another person in a group and maybe I'm struggling in one part and I'm good in the other part. So maybe I take the section I'm good at.
Sure, that works. That's sure. You don't have to contribute to it shouldn't be 50-50. So let's say you are doing an experimental plus a numerical work. You are good at numerical work. You do the numerical parts. I mean, this doesn't happen because it's too much of a project for the course, right? And your teammate takes care of the experimental part. So this can is that what you asked?
Okay, it's fine.
What was the question?
So the question I want to ask is for the group project that people have been doing, so in a group they divide it based on their strengths.
Yes.
And maybe someone that knows a particular section like the numerical part or maybe the main part
Okay.
take the numerical part. Then what if the other person is not talking the numerical part, maybe take some section. Then during the presentation it's gonna show that this person did better work.
Yeah.
I would think if the two of them have to come up and
Let's say you are presenting your work and you have done the numerical work and your teammate has done the other work, whatever that is. You are going to present the numerical part of it, your teammate is going to present the other part of it.
okay. So the person's presentation will not affect the other team member presentation. Like if someone is presenting
So you are asking me if your teammate does a bad job, is it going to affect your grade?
No, the person I'm asking is in the presentation there are some sections that are very important like numerical.
No, I understand. So that is what you're asking. If your teammate does a bad job on explaining, is it going to affect the other person's grade?
What I'm asking is if a teammate takes simple part of the project because that is the area he thinks that he can do, and the other teammate takes the hard part, and both of them defend it.
You are not gonna get more credit for doing the harder part because that is on you, right?
Okay.
You have to do the management, right? If you feel like you are pulling more weight, you have to talk to your teammate, right? Does it make sense? Okay. And it is a very important part. So the reason I pushed for teammates is because you can handle these situations that will come up in the real world. I'm pretty sure you have all came across these type of situations that you are doing more work than your teammate or you are abusing your teammate. Yeah? We can be on the both end of it. Is that what you were talking about? We can talk later. If it wasn't your question, we can talk later and come back to it. Any other questions? Okay, let's go back to the lecture. We were talking about fins. Right. We started solving a partial differential equation for a rectangular, or the heat equation for a rectangular fin. Let me draw this again. We have a rectangular fin with a constant area, and we want to solve the equation for this rectangular fin. And we came up with this partial differential equation, partial squared theta partial x squared negative m squared theta is 0. Do we remember this part? Okay. Do we have anyone who has some issues getting to this equation?
Yes.
What is the issue? You don't remember it. Okay, let's go back. So we
I had a problem with this part last session.
Okay. Let's go back a little bit, just do a review. This was the main equation, right? You remember this, right?
Yes.
The idea was we are dealing with a rectangular constant area thing, so this part became the perimeter, right? Surface area divided by the length, the perimeter of the fin. So we replaced it with P. So we had dt squared, d squared t, dx squared minus hp divided by ac k. And this is t minus t infinity equals to 0. To simplify things, we introduce these two new parameters, theta and m squared. When you plug them in, you'll get to this equation. Is it clearer now? Okay, so let's start from here. The main question we have right now is that can we solve this partial differential equation? That's the main question we have to answer. And the answer to that question is yes. Do we need to know how to solve this equation in this class? And the answer to that question is no. You just have to know the final general solution to it, right? And so the assumption we have in this class is that you know how to get from this point to that point, but you will never be examined on this. So I'm just going to take you at your word that you know how to get here. So theta is your general solution. Theta x is going to be equal to a constant, let's call it d1, hyperbolic sine of mx plus d2 hyperbolic cosine of mx. I'm hoping we remember the hyperbolic sines and hyperbolic cosine, the hyperbolic things called in general. Yes, we do remember. Okay. Just as a refresher, hyperbolic sine is essentially e to the power x minus e to the power negative x divided by 2. And hyperbolic cosine is e to the power x plus e to the power negative x to the power divided by 2. So this is the general solution to this type of equations. What is the type of equation that gives you this specific general solution? It's a second order equation, d squared theta dx squared. It's the second order part of it, which is equals to, I'm just going to take it to the other side. It is equals to a positive constant multiplied by your variable. That's very important. So this will give you these type of general solution. Okay? So how can we find these constants? Boundary conditions. We don't have any initial condition here because it is a steady state solution, right? So what are the boundary conditions? When it comes to yes. The distance and temperature. I'm not sure what you mean. Okay, exactly. So we're gonna have, it's a one-dimensional heat conduction, so we need to have one boundary here at x equals to 0 and one boundary here at x equals to L. What is a boundary at x equals to 0? The boundary at x equals to 0 is always the base temperature boundary. That's the assumption. So we are going to assume that theta at x equals to 0 is equals to T of B. I'm sorry. And since we have the solution for theta instead of T, we are going to have theta of 0 is T of B minus T infinity. That was the definition of theta. Theta of B. Okay? So this is one boundary condition. What about the other one? For the other one, the other side, the tip of the fin, we can have different situations. We can have actually a convection boundary condition. Or a Robin boundary condition, right? Which is negative k partial t partial x at x equals to L is equals to your heat transfer coefficient multiplied by t minus t infinity. And we can rewrite this in terms of theta. So partial theta partial x as equals to L is equals to h theta. Of course, this only talks about temperature at the tip, so this is going to be theta of L. There is another type of boundary condition, an adiabatic boundary condition. What is an adiabatic boundary condition?
Doesn't mean that the end is an insulator.
Exactly. The end is insulated. So in terms of theta, d theta dx at x equals to L is 0. Third boundary condition is a fixed temperature boundary. Which essentially tells you T at L is equals to a constant number, T of L, which is the same thing for theta. Theta of L is going to be TL minus T infinity, or theta of L. Okay. Yes.
Could you explain again the adiabatic boundary?
What is an adiabatic condition in general?
There is no heat loss or
There is no heat transfer, right? Which means that the temperature gradient is 0. That's it, in that direction.
so, what benefit does it give us to assume that in this scenario?
It is not necessarily a benefit, it's a condition. Let's say you have your fin, the fin tip is exposed to insulation. You still have a lot of convective heat transfer around the fin, right? Which is extending your surface area. You always, when you are dealing with fins, the tip condition is not the most important part of it. When you are dealing with fins, this extra surface is the part of it. But if you didn't have this, then we only had heat transfer from this square, right? But we have extended the fin, so we are essentially increasing the heat transfer area. The boundary may have insulation based on your situation, right? May have any sort of condition. But let's actually talk about these conditions. We understand the convection condition. If it's just freely, just free in air, right? You have a fin like this right here. Then it is exposed to convection, right? We have air movement here, probably. We don't have that much of movement here, but it is exposed to convection. What is the real situation in which we can get a fixed temperature boundary? A fixed temperature, this boundary. How can we get this boundary in the real world? Yes.
I think it's at the end of the film because there is conduction and convection at the same point.
We are talking about the fin tip condition, right? I mean, well, it's more of a general question. How can we maintain temperature at a location?
Heat in is equal to heat out.
No. I'm talking about the real world applied thing. Not no equations. How can you maintain the temperature at a certain location? If you heat it up, what's going to happen? Are you going to have this constant temperature? No, your temperature is going to increase. So how can I keep a constant temperature?
Put a heat sink. Use a heat sink in a particular location.
A heat sink and a heater?
If you want to maintain the temperature.
So you basically what you're saying is that we have to maintain the heat flux. We have to have variable heat flux.
No, it should be constant, like the amount of heat that is coming in.
But that means the temperature is going to change.
No, like yeah, you have to balance it out accordingly, like as amount, like if you have X amount of coming
Give me
in.
a real world example. A constant temperature boundary.
Insulation. If you have insulation.
Insulation is an adiabatic condition. It is not a constant temperature. Think about it. What is the real world situation in which you get constant temperature, no matter what the heat input?
The ambient temperature is equal to.
In the ground, not necessarily, no. Ambient, but I'm not sure what you mean. It should be easier, guys.
Cool it up, I guess radiate.
Cool it and heat it at the same time. You just play with heat flux, yeah, but it is not a real world situation, right? You may have some temperature sensor there, right, and expose it to convection and like heat it up, right? That definitely works. But then a simpler real world situation. What is that a specific type of flow or a situation, whatever you want to call it, that maintains a constant temperature throughout?
Through the vacuum?
Yes.
About boiling water.
Boiling water, that's a very good example, right? That when you are during phase change, you are essentially maintaining a constant temperature. It can be solidification or melting, or can be boiling evaporation, right, or condensation, right? But so you see, when you expose your fin tip to a boiling water or condensing water, you are essentially maintaining. It is not a very accurate description because there is always plus minus 10 degrees temperature variation, but it's a very fairly good assumption that we are going to maintain a constant heat flux. Also, you can maintain temperature in a furnace, but that is based on that sensor thing that you were all coming up with, right? We are reinventing a build here. If you essentially usually have a sensor in a furnace, you can just change the heat flux to maintain a temperature, right? Okay, so that is, let's put that out of the way and continue. There is another type of boundary condition here that is specific to fins, and that is called an infinite fin. Infinite fin. Which happens, we assume we have the infinite fin boundary condition when you are M, and we define M as a square root of HP divided by KA, right? M multiplied by length of the fin is larger than 2.65. It sounds like an arbitrary number, but it's not. You can do some calculations and essentially do a certainty analysis to get to this number. Well, what is the situation here? What do we get for a fin? When we say it is an infinite fin, what does it mean?
The length is larger than the width.
The length of a fin is usually larger than, in general, it is larger than a fin. It is usually larger than a fin. So it is probably always the case, yes.
That the tip temperature is equal to the ambient temperature?
Exactly, that is the point. So this is the point at which, no matter how much heat transfer you have, how much heat input you have, what is your base temperature, you have reached a zero heat transfer situation, essentially. It is not insulation, but temperature. The reason you have zero heat transfer is because temperature of the tip is equals to the ambient temperature, right? Which in terms of theta, it means your theta is going to be 0. So we have one boundary condition for the base and 4 boundary conditions for the tip. How many general solutions can we have here? 4, right? We have 4 different boundary conditions. And here we are going to do the solution for the adiabatic boundary. So we are assuming that is the tip is in, that's a very important point, guys. The tip is insulated. Around it, we still have convection, right? If around it was insulated, then it wasn't a fin. It was just a rod with one-dimensional heat transfer, right? Okay, so I am going to give you the final solution, but I'm assuming you know how to get to this point. Theta over theta b is going to be hyperbolic cosine of m, and this is the temperature distribution, right? Multiplied by L minus x divided by hyperbolic cosine of ml. So this is your temperature distribution. The fin heat rate can also be calculated using this equation. How can we calculate the fin heat rate? This is a rectangular fin, constant cross section. How can we calculate the fin heat rate? And it's also a solid. Conduction, the Fourier's law, right? That's what you meant. So negative k, d AC, of course, d theta dx, and at x equals to 0. So you take the derivative of your theta, and you have the conductivity and cross-sectional area, which means you should be able to find the Q infinity. Q of f. You should be able to take the derivative and find the Q of f. For the rest of boundary conditions, you are going to get 3 bonus points if you find the solutions yourself. Next lecture, I'm going to provide a table on Blackboard with the solutions. And if in an exam, if you had a fin question, you can bring those solutions, right? You don't need to derive the equations on an exam. But yeah. So for the 3 different boundary conditions, the infinite fin, the convection, and fixed temperature, give me the solutions, which essentially means that plug in these boundaries into this general solution here, find D1 and D2, and then find the QF, and you'll get 1 bonus point for each submission for like each of these conditions. So if you submit all 3, you will end up with 1.5 point out of 100 of your final grade. Okay? So if your peers give you 0, you'll make a 1.5 point of it for your project. Okay, any questions? Let's move on. Let's say we have an array of fins. How should we deal with these? And let's say I ask you to find the total heat rate out of this plate, this whole plate. It has 3 fins on it, and it has an array of fins, right? How should I deal with these?
Do they affect each other?
That's the question. Do they affect each other? How should I deal with them? How should I find the total heat rate? Does the heat transfer here affect the heat transfer here? Which essentially, if they do affect each other, means that you have a 2-dimensional heat transfer, right? Because you have heat transferring in another direction.
Can we assume they do not?
Well, you have to be able to back up your assumption, right? Why would you assume that?
Sir, all of them are the same material and getting heat at the same flux, right?
So for fins, we can safely assume it's a one-dimensional thing, so that it doesn't really affect the surroundings, because that's how we have treated fins, right? One-dimensional heat transfer. And since we have conduction and convection on the base, we only have heat transfer between these bases, between these parts of it. Let me actually do a two-dimensional drawing. It'll be easier to explain. The heat transfer between this base, there will be heat transfer between this base and the surrounding air. That's it. Right? So we have heat transfer in this direction, one direction, transfer in this direction. So they can be treated as separate heat transfer mechanisms. How can we combine them with each other? The point is, at this point, we have T infinity. At this point, we have T1, right, or T base. How can we combine this array of fins with each other?
Treat them as parallel. Treat them as the parallel one with the
This is exactly. This can be treated as a thermal resistance case. So as long as we can come up with a formula for the resistance of a fin, we already have the resistance of the base. It's just a regular convection resistance. It's 1 divided by h around the base here, multiplied by the area of the base. So we need to come up with a resistance formula for the base. We define this resistance formula as 1 divided by efficiency of the fin, multiplied by h around the fin, multiplied by the area of the fin. So how effective is the fin in heat transfer is going to affect this. So essentially, we are treating this as a regular convection, but we are including the increased heat transfer due to the presence of the fin in this efficiency calculation. But how can we calculate the efficiency of the fin? Of course, it's going to be equal to the Q of fin divided by the maximum amount of heat transfer possible from that solid rod, right? If it wasn't the same. And what is the maximum amount of heat transfer possible? The maximum amount of heat transfer possible is your heat transfer coefficient multiplied by the surface area multiplied by the theta of the base. How is this the maximum amount of heat transfer? We understand the Q fin, right? Q fin, and for adiabatic condition, let me actually give you the formula. It is M, capital M, tangent hyperbolic of a small ml, and capital M is HP ACK, the multiplications of all of these, and a square root of this. So for adiabatic fin, we already have the total amount of heat rate out of the fin. So we have one part of the efficiency calculation, right? The other part of the efficiency calculation is the maximum amount of heat transfer possible, in theory, from this fin. And I say we can calculate this maximum amount of heat transfer by multiplying the heat transfer coefficient around the fin, so this is h of f, by the surface area of the fin, by the theta b, that's the Tb minus T infinity, right? How does this represent the maximum, theoretical maximum, a heat transfer of the fin? Or if you think this doesn't represent it, in order to find the efficiency, we have to divide the total heat rate by a maximum, by a nominal maximum, right? How can we find that maximum? Any ideas? Let's actually back up a little bit. Do we all follow what is going on here? Do we understand why do we need this maximum? Yes or no? I see some heads nodding, but the others just are looking at me with dead eyes. Is this clear? Why are we looking at this efficiency? Right? Is this clear? Yes? Okay. So, and we understand the efficiency is some value divided by the nominal maximum value, right? That's always a definition of efficiency. So, we have to divide the total heat rate of the fin, which is the real heat rate of the fin, divided by the maximum heat rate that is possible out of that solid rod. How can we calculate that maximum heat rate possible? Let's say your T base is larger than T infinity, right? How does this represent the maximum amount of heat rate out of this solid rod?
If the base temperature was the same throughout the fin, it would be the greatest difference against the ambient temperature.
Exactly. Thank you. So in order to have the maximum amount of heat transfer throughout, we have to have the greatest temperature difference, right? And what is the maximum possible greatest difference is when you have all of the rod as temperature of the base, TB. Does this make sense? Is it even possible? Sure. If you have a fast enough conduction heat transfer mechanism, this can happen. I mean, not in real world, but is you have a very conductive solid, infinity conductivity, right? Then yeah, you can have TB all over this, and then you can have a maximum heat transfer. If it's not clear yet, I remember this was very confusing to me when I was taking in my heat transfer class. That's why I'm focusing on this. So this is TB, this is T infinity. TB is larger than T infinity. What do you think the temperature would be here? Less than TB, more than T infinity, right? So we will have some heat transfer, which is less than TB, less than, our T is less than TB, more than T infinity. Which means that the heat transfer here, let's say this is 50% less than TB. So if you were to calculate the heat convection here, it will be HAT minus T infinity, right? But if the value here was TB, it would be HATB minus T infinity. And this is going to be much bigger than this, right? Which means that you have a higher rate of heat transfer using this. So in an ideal case, if you can have base temperature spread throughout the fin, you are going to have the maximum heat transfer. Is this clear to everyone? Okay. So let's move on. So we understand how to find the efficiency based on the heat rate of the fin. And using that efficiency, we are going to calculate the thermal resistance of the fin, right? And these are all parallel to each other. So this will be treated as a system of parallel resistances. And how did we find the total resistance of a system of parallel resistances? 1 over R total would be equal to, exactly, 1 over RF plus 1 over R base plus 1 over RF, 1 over R base, and so on and so forth. And the thing, since we are going to have the same fins and the same bases, the same distance between them, we can just say N over RF for the number of fins and N over RF for the number of bases, right? So that's just, you're going to just add them together. It's just a mathematical thing we can do. And then we can set this equal to 1 over eta naught HA, which is going to give us the overall efficiency of the fin array. If I want to rearrange this equation for eta of O, the overall efficiency, this is what it's going to look like. It is going to be equal to heat transfer coefficient at the base multiplied by the total area of the base. So this area plus this area plus this area, all of these areas, plus the number of the fins multiplied by the efficiency of the fins multiplied by the H of F, area of the fins divided by H multiplied by total area. Any questions? No.
For the total resistance, the numbers of fins was you had the number of fins in the numerator in the middle of it, and then, right? Is that what's in the numerator?
Here,
Yeah, number of fins.
this is the number of fins, and this is you can actually combine all of the bases together and have 1 over RB. So you can combine all of the areas here, where it's going to be the exact same thing. And it will present all of the base areas. But if you wanted to have them separately, it would be n divided by R of F plus m, the number of bases. Let's call this m instead of n, because they may be different, right? There may be 1 or 2 more. Yes.
Can you show on the thing that very exactly it would be
Okay, sure. So this is the fin array. These are your fins. HB and HF are usually the same thing because they are the same. There is the same fluid around base and the fin. But HF is going to be the H around here. HB is going to be H of the base. Let's say you have some fluid flowing over these fins. You will probably get a different heat transfer coefficient here than the base, because there will be less fluid movement on the base, right? Your heat transfer coefficient will be definitely different inside that boundary layer. We actually have to do some calculations to calculate the heat transfer coefficient there, but you will be able to assume some overall heat transfer coefficient for the fins. Okay. If there is no other questions.
Sir, in this case, we're just taking 3 fins and 2 bases, right?
It really, I mean, if your system is like this, then it will be 1 base, 2 base, 3 base, 4 base,
Okay.
right? And 3 fins. But if your system is like this, it really depends on your system, right?
So like in the previous example where we have a singular fin, so how do we know, would we mention that we are not supposed to take any base, or like in the singular fin, there should be essentially, according to this logic, 2 bases, right? Above and below.
Yes, yeah.
So would it be mentioned that we are supposed to take them or not?
So if you get an example, it will look like this. Let's say this will be your base, and then it will be a system like this. So you should be able to figure out how many bases.
Or
You will be given a complete a structure to work with. Okay, let's move on. So next logical step, since we have dealt with the one-dimensional cases, next logical step is to move on to multi-dimensional cases, right? And for the multi-dimensional cases, we first need to talk about different coordinate systems. What are the main different coordinate systems that we usually deal with? What are those?
Cylindrical?
We usually start with Cartesian, right? The easiest one. And the most common one, Cartesian coordinate system. And for the Cartesian coordinate system, we had the heat equation as rho Cp partial T equals to negative k. I'm sorry, not negative. Partial x of k partial t partial x plus partial x of k partial t partial y plus partial y of k partial t partial z. Plus a q dot. This can be your heat source. Okay, this is the Cartesian coordinate system. And the Fourier's law in Cartesian coordinate system is going to look like this. Negative k partial t partial xi, negative k partial t partial yj, negative k partial t partial z k. Next coordinate system, as John mentioned, is the cylindrical coordinate system. Cylindrical coordinate systems are actually very common, but they're a little harder to deal with. And by harder, I mean it's just there are more terms included. It's a little harder to master cylindrical coordinate systems, and we don't really, in our education system here, we don't really talk about them that much. So, and here we are. I'm just going to give you the final equations. So, or what are the axes in the cylindrical coordinate system? Theta, right? Angle, right? And there should be three, right? There should be three axes, the general axis.
Theta, R, and Z.
Theta, R, and Z, and also, so it should be like a cylinder. R, theta is this one, and Z, it can be in this direction or in this direction, doesn't matter. So we are going to have three axes. And the same as Cartesian coordinate system, we need to have three axes. So we are going to represent Fourier's law in the cylindrical coordinate system like this. It's going to be negative partial t partial I, and we are going to use I of r for the unit vector in the r direction. Then negative k over r partial e partial t partial theta j of theta, then negative k partial t partial z k, which is the same k. Can be k of z or regular k. Can anyone tell me why do we have that extra r there? Why do we have this extra r?
Which
Make sure you see this, because if you don't, then you are dealing with just regular Cartesian coordinate system.
What algebra is the, I don't know how to say that, calculate
there is temperature gradient within R with a different angle.
There is gradient. She was actually correct, and you're not wrong as well, but you didn't really answer this question specifically. So we are talking about the gradient on this arc, right? And on this arc, the gradient is dr. Let's call that length of this arc. Let's call this s. Is d of s. How can we calculate this s? Is r multiplied by theta. So it is dr of theta. And we assume, I'm simplifying things. So we are going to assume r is constant for this specific case. We are going to end up with r theta. Again, I'm simplifying things just to make sure. That's why we have this extra r here, because the gradient is the changes of the that your small element, heat flux on your small element from this location on this location to this location moving on this arc. That's the length we are passing through. Okay, so based on this, we can rewrite the heat equation. Rho Cp partial T equals to K divided by R partial R of R partial T partial R. This is a little, of course, looks a little different. K divided by R squared partial squared theta partial theta squared plus K partial T squared partial Z squared plus Q dot. So heat equation in cylindrical coordinate system. What is the next coordinate system that is very common?
Spherical.
A spherical, exactly. So a spherical coordinate system. What are the axes in a spherical coordinate systems? What are the axes in a spherical coordinate systems?
Theta, phi, and r.
Theta, phi, and r. Exactly. R, theta, and phi. So we are essentially on a sphere. And I'm going to draw the Cartesian coordinate system for simplifications here. Let's say we are pointing at this point. This will be your R. This angle that the projection of R makes with the xy plane is going to be theta. And then this angle between R and the z-axis is going to be phi. So the definition of theta is a little, I'm sorry, this is phi, this is theta. This is the other way around. This is phi, this is theta. Definition of theta is a little different from the Cartesian coordinate systems, from the cylindrical coordinate system, so keep that in mind. And based on the same idea, we can find the Fourier's law as negative K partial T partial R I of R minus negative K divided by R partial T partial theta I of theta minus negative K R sine of theta partial T partial theta I of phi. And the energy equation is going to look like this. Rho Cp partial T equals to K over R squared partial R of R squared partial T partial R plus K over R squared sine squared of theta partial T partial phi. This is squared. And K over R squared sine of theta partial T partial theta plus a Q dot. This is a doozy of an equation. It's a very long equation. So just try to, I guess, write it down and have it with you on an exam.
Plus Q dot on the end.
Pardon me?
Plus Q dot on the end.
Yes. It is always plus Q dot. That's the heat source, right? And there is also 2 bonus points here. If you derive the equations in the spherical and cylindrical coordinate systems, you'll get 2 bonus points. So next time when you come in, you can get to up to 2.5 points of your final grades. Final grade.
Is the what is it, the middle term, is that the second derivative?
Yes.
For both spherical and.
So if you recall, this is the one derivative, second derivative, but we have combined the second derivative here.
Yeah, so it's t squared.
Yes, that's t squared.
Deriving spherical and.
And cylindrical.
Cylindrical.
1 bonus point for spherical, 1 bonus point for cylindrical. I'm pretty sure you can find the derivations online. Okay. One quick note though. So I in another class, not here, I told the students that the derivation is this in the book. Just go there and copy it and bring it to me. And one student went there and took pictures of the PDF file and copied. I'm serious. And copied it in the Word and just sent the PDF. That something like that is definitely not acceptable. The reason is I want you to write this down by yourself and I want you to try to understand the logic behind this derivation. Like being able to do the derivation is not important, but understanding the energy balance that will give you this derivation is important. Yes.
What did you call it? Heat transfer in cylindrical coordinates.
Heat equation in cylindrical and spherical coordinate systems.
Do we have to know it very well, like before?
What do you mean by that? Know it very well.
What you before you said that.
Oh no, it is not like the other. I mean, you shouldn't ask this question. My expectation is for you to know this, right? Well, we have an agreement that I'm not going to question your knowledge, right? So, but yeah, sure. If you want to submit the bonus point, my assumption is you know this. Yes. Where are you? Okay, here. Heat flux. Yeah, no. That's theta. Thank you. Okay. Okay, so let's move on. Let's move on to a simpler case, a two-dimensional. I guess we are going to start this, but we are going to continue this during the next lectures. Next lecture specifically. A two-dimensional heat conduction equation. So two-dimensional, a steady state, no heat generation, heat conduction equation. What is the governing equation for this in Cartesian coordinate system? This is the general governing equation, right? The heat equation. How can we simplify this equation to fit our problem? What are the simplifications we can apply here?
2D, not 3D.
2D, not 3D, so the Z part can go out. What else?
No heat source.
No heat source, exactly. What else? A steady state. Temporal term is also gone. We are going to assume conductivity is constant, so we can take it out of the derivative, right? So you are going to end up with K partial squared T partial X squared plus partial squared T partial Y squared equals to 0. Okay. And there's also a K here. And we can also take the K's out. And it will be partial squared T, partial X squared plus partial squared T, partial Y squared equals to 0. Or del T is 0. which is the Laplacian equation. So we want to find a general solution, or a specific solution actually, a closed form solution for this problem. And as at this point, I'm pretty sure all of you are familiar with the separation of variables method. We are going to use the separation of variables method to do this. What does the separation of variables tell us? It says t, which is a function of x and y, can be separated to two functions, a multiplication of two functions, x as a function of x, a small x, and y as a function of a small y. And we are going to put this in the governing equation. So we are going to have partial squared x of x multiplied by y of y, partial x squared, and partial squared x of x, y of y, partial y squared equals to 0. Can we take this derivative? We have one yes.
We need to separate them first.
Separate them first. How would you separate them? They are separated, right? I'm not sure what you mean.
Because the first one is a function of x and y, so we need to separate the x with the x and y with the y.
We need to take the derivative first, right? That's the first step. So here, this is a function of y multiplied by a function of x. So this is treated as a constant, just comes out of the derivative. And for x, we are going to have the second derivative of x, or x double prime, multiplied by 1. This is going to be the first term, plus x multiplied by y double prime. This is equals to 0. Next step is to take one of them to the other side. And then I'm going to put x's on one side, y's on the other side. So we're going to get x double prime divided by x is equals to negative y double prime divided by y. Okay. So what can we say about these two functions?
They should be equal to a constant.
Why?
Because this is x and this is y, so they can be equal to each other. They should be equal to a constant.
So what Muhammad is saying, I assume, that this part of this function is only a function of x, right? This is, right, we have x double prime, which is only a function of x. We also have x, which is a function of x. This part of this function is a function of y, right? How can this be possible? A function of x to be equal to a function of y?
They are equal to a constant.
They are equal, both of them. This ratio has to be equal to a constant. And we are going to call that constant lambda, or lambda squared. Let's do lambda first. Okay, it is 2:30. So let's just wait here, and we are going to come back on Tuesday and pick this up. Is there any questions about the project, about the course? One note though, please do not talk to each other during the lecture, because this brings me off my balance. This takes me off my balance, right? It's really, I can't concentrate when you're talking to each other during the lecture. Please don't do this. Any question? Yes?
I'll need to break that.
Sure. Yeah.